Good evening. My name is Sivam Kumar from Section P. I'm from SRM University AP. So my project topic is MaxScore algorithm optimized for high-speed rank retrieval in inverted index. It is also known for making search lightning and fast. So let's come to the introduction. Imagine you are a librarian in a massive library with a million of books, and come someone asks you to find top 10 books of artificial intelligence. Now you could check every single book, score each one based on how relevant it is, and then pick the top of it, like top 10. But that would take forever, right? What if I told you there is a clever trick that lets you to skip the most book entirely? While I still guaranteeing you to find except same top 10. Exactly. That's essential while MaxScore algorithm does for searching engines. Think of it the way. You are looking for tallest people in a room and you only care about top 5. If you have already found 5 people who are 6 feet tall, why would you waste time to measure someone who clearly only 5 feet? Max score algorithm applies the same early stopping logic to document retrieval, making search dramatically faster without sacrificing accuracy. So let's come to simple example. You are searching a chocolate cake recipe and you want top 3 result. What will you do? So these are the 5 6 steps which will known what we can do. You have already found 3 documents with score 45, 42, and 40. So your current threshold is 40 because it's lowest among 3. So now you are now looking for new document that mentions chocolate but not cake or recipe. Before even calculating its full score, you can estimate all best. This document can score 35. Since 35 is less than 40, you skip the document entirely without wasting the time on the full calculation because, of course, the lower one will not be the answer. This is the max score brilliance. Skip the document that couldn't possibly make it into the top result. So we can say the formal definition of max score is dynamic pruning algorithm for top K document retrieval that safely skip during query processing by maintaining an upper bound on maximum possible score that unscored the document can achieve. So these are the four key components. First one is top K heap, maintaining the current top K document and their scores. Threshold theta, the kth bit document found so far. Max score algorithm, pre-computement, maximum contribution, and each document term across all documents. Safe filtering. Documents are skipped if their maximum possible score are less than theta. So let's come to the formula section now. For a query Q is equal to T1, T2 up to n document and document D score the value D comma Q is equal to sigma of I is equal to 1 till nth position W D comma D. This is the formula to find the score. We have weight as T1 comma D is the weight of the term Ti in document D. Finding my max score in term Ti is max score Ti is equal to max of weight of Ti comma D belongs to small d belongs to upper D, capital D. Upper bound for document D. Upper bound D comma Q belongs to sigma max score Ti for all the term that appear in D. So Ti belongs to Q, small q. And this is the pruning condition. Skip the document D if upper bound is less than equal to theta. We don't have to find the minimum score, right? The score will be obviously the higher one. So we have to skip the document where theta is the score of the kth best document currently in the heap. Now let's go to the algorithm section. So this is the max score algorithm where we will take input query q is equal to t1 t2 up to nth term and the desired result is k. Output we want is top k documented ranked by score. So this is the first step is initialization. So create an empty heap top k underscore heap of size k. Set threshold theta to 0 for each term t1 belongs to q. Compute max score. Sort the posting list by max score ti in ascending order. Now process each candidate document. This is the second process. Here's the part wise. Part A is compute upper bound. Upper bounds minus max score for all term ti present in document D. Check the pruning condition. If upper bound D is less than theta, skip the document because the minimum one definitely will not be the answer. So let's come to C. Otherwise, calculate and update actual score. So what is the formula of actual score? Actual score belongs to weight. Now we have to update the heap. Let's come to the if condition. Top heap dot size is less than k. Then we have to insert the score in the document and then update the theta. If the score is greater than theta, then remove the minimum and insert the current score and then update the theta. Now the last step is to return the result top k underscore heap score but in decreasing order. So let's come to graphical example. Now let me illustrate how max score work visually. So let's take a query machine learning. We will take term t1 as machine and t2 as learning. So we need k is equal to 3. We want top 3 documents pre-computed max score. So graphically query is machine learning, t1 is 15, t2 is learning, which is 20, and machine is 15, sorry. So max possible score can be 15 plus 30, 35 the max score possibility. So visual representation is 15 for machine, 20 for learning, and max score is 35. So let's come to process document now. Document 1 contain both, which is machine plus learning, which is 35. So actual score what is 12 plus 18 is 30 added to the heap. Now heap have the value of 30 and which is greater than 0, so we have to add it in the heap. Now let's contain both term. Upper bound is 15 plus 20 35, and actual score is 15 plus 20, which is equal to the heap. So what is in the heap now? 30 and 35. So we have to take the lowest in these both, so which is 30 is the lowest one in these. So now we will take theta as 30. Document 3 contain both terms. Upper bound is 35 as usual. Actual score is 14 plus 17, which is 31 added to he because it is greater than 30. So now we have to take minimum between 30, 31, and 35, which is 30. So now let's come to document 4. Contain only machine. Upper bound is 15, and which we have to skip because 15 is less than 30 because it cannot beat the threshold. So there is no point of taking machine as upper bound. Now coming to document 5, which contain learning upper bound, which have 20, and this also we have to skip because it is less than 30, so it have no point, it cannot beat the threshold. Let's come to document 6 where they contain both the terms 15 plus 20 machine plus learning, which is 35, and actual score is 32. So remove document 130 and we will add document 632 because 32 is greater than 30. Now what we have in Lee heap 31, 32, and 35. So 31 is the smallest among them. So this is the theta and so on. We will repeat this till we find the heap value. Let's see the score distribution. Like we have document 1 which is till 35, and then we got as 40 as answer. So we have selected document 2 and removed document 4 and 5. Let's come to numerical example now. Query data science and Python. Term 1 is data, term 2 is science, and term 3 is Python. We want top K2 element and we have 6 document as you can see here. So now we will pre-compute max score. This is the step 1, which data can be highest 10, science can be 8, and Python can be 12. So as we can see, data is max 10, science can be 8, so maximum is 8, and all the document are less than 8. Same as 12, all the document are less than 12, not greater than 12. So now let's come to query processing D1. Upper bound is 18, theta is 0 as of now, and 80 is in greater than 0, so we will add in the heap. So now we have to find the score D1. 8 plus 7 plus 0 is 15, which is we will add in the heap. Now theta is updated, value 15. Now process document D2, upper bound is 30, theta is 15. Of course, 30 is greater than 15. Now we have to find the score. We will get 30, and we have the value 15 and 30 in the heap. Now we have to find the minimum value, which is 15. So we will proceed with the value 15. Now let's come to process D3. Upper bound is 22, of course greater than 15. Now we will again check the score of D3. So here heap is full because k is equal to 2, d3 is 15 equal. Both previous score of heap and current score is coming 15. Now heap is full. So what we will do? We will not update the heap because the value are same. No point of updating heap. Now let's come to D4. Value is 20, of course greater than 15. Now we have to find the score, which we are getting 17. 17 is greater than 15. Now we have to remove 15 from D1 and add D4 as 17 right now. So what we have left in heap, 17 and 30. So now which is minimum? 17. So we have to update the theta. Theta is 17 right now. Let's come to process D5. D5 is 18, theta is 17. Of course 18 is greater than 17. We have to find score again. We will get 5. 5 is less than 17. So skip because no point of going further. So no change in the heap. Last document we get upper bound is 6. Theta is 17. 30 is of course greater than 17. Find the score. So we will update the heap, remove 17 from the data and add 24. What we left in heap, 24 and 30. So theta is 24. So the final result of top two document is 20. D2 score 30 and D6 score 24. Let's come to efficiency gain. The additional approach calculating score of all six documents is equal to 6 calculation. Max score approach calculation scores for document 5. D5 was skipped and 5 calculation, saving 16.7% fewer calculation, which is much relief. Let's come to the conclusion. The MaxScore algorithm is the game changer of high-speed document in retrieval information system by intelligent maintaining upper bound on document score and dynamically adjusting the threshold. It allows engines search engine to skip the vast number of document possible and top k result. These are the key points. First is dynamic pruning, guaranteed correctness, threshold and filtering, composition, pre-composition key, trade-offs, real-world impact, and last one is scalability. So we can say all about this is max score is the elegant answer of fundamental question in information retrieval. How can we find the best result without looking at everything? By combining the upper bound estimate with dynamic pruning. It achieves both accuracy and speed, the holy grail of search engine optimization. Thank you for my time. This was all about my topic. Thank you.